Hello students. Today we are going to discuss about expression for induced EMF by using Lorentz force. We have already discussed in the previous class the expression for induced EMF. So what is the expression for induced EMF? E equals to BLV. But here we are going to discuss the same expression using Lorentz force. So what is Lorentz force? Lorentz force is the force that is acting on a charged particle when it is placed in the magnetic field. And this we have discussed in moving charges and magnetism. What is the force that is acting on a charged particle when it is placed in the magnetic field? It is F equals to QVB. This is the maximum force that is acting on a charged particle when it is placed in the magnetic field. So using that force, how to calculate the induced EMF? That we will see. So to derive this expression, consider the same thing, that is a rectangular conductor PQRS, and that is placed inside the magnetic field. The length of the conductor is Sx and the breadth of the conductor is L. So the area is L into X. That and all we have already discussed. And here we also have considered a special case, that is this end is not fixed, it is movable. So this conductor PQ is moving in the magnetic field with a velocity V. When this conductor is moving with a velocity V, there are few charged carriers on the conductor PQ that are moving from P to Q in the magnetic field. Because here you can see this is a current carrying conductor. See, this arrow indicates the direction of the current. See, when current is passing through this conductor, I can say current is passing from P to Q. What is current? Current is the rate of flow of charge. So I can say that the charged particles are moving from P to Q. So when a conductor PQ is moving in the magnetic field with this velocity V, the charged carriers are moving in this conductor from P to Q. See, the rod moves with a speed V towards the left, then charge will also be moving with a speed V from P to Q, and where is this? In the magnetic field. So the charged particles are moving in the magnetic field. So when the charged particles are moving in the magnetic field, they experience some force. The maximum force that is acting on that charged particle is F equals to QVB. So the work done in moving the charge from P to Q is, we know work is force into displacement. Here the charged particles are moving from P to Q, that means they are moving in the conductor of breadth L. So I can say charge is moving from P to Q in the sense it is moving across a distance L. So work is force into that displacement L. So W equals to F into L. What is F? F is the Lorentz force, which is QVB. That is the force that is acting on the charged particle. So we can write W equals to QVB into L. Then what is EMF? EMF E is W by Q. We know electric potential is work per unit positive charge. Here EMF is acting like a voltage. So EMF E equals to W by Q we can write. So this is the expression for EMF, and we know what is work. So substitute this equation in this equation. So if I substitute this equation in this equation, what we get? E equals to QVBL by Q. Then this Q will get cancelled. Then we get E equals to VBL, which is the expression for induced EMF. The same expression we got, but here we derived using the Lorentz force, which is F equals to QVB. And the next topic is energy consideration. So here we know already induced EMF, motional EMF expression is E equals to BLV. So what will happen, how the energy is produced, we are going to discuss in this. So the same thing we are considering. Let us consider a rectangular current carrying loop that is placed in the magnetic field. Okay, here let us consider R is the resistance of movable rod PQ. We have discussed already, this is a movable rod, it is not fixed. It can be moved in the magnetic field with a velocity v. So R is the resistance of that movable rod. And also consider the resistance of other arms. That means RQ and SR. This SP resistances are very negligible. So if all are very negligible, the resistance of this PQ is R, then I can say the total resistance of this rectangular conductor is R only, because all these values are negligible. Only the resistance of this PQ is considerable. So the resistance of this rectangular conductor is R, we can say. And in current electricity chapter, we have discussed that I is V by R. And V, it is here EMF act like V. So we can write I equals to E by R. We know motional EMF is BLV. So that equation only I am using, E equals to BLV. Now substitute this equation in this equation. If I substitute, we get I equals to BLV by R. So from these two equations, I got the expression for current in this loop. Okay, so current equals to BLV by R. Consider this as equation number 1. Now, we know this also. This also we have discussed in moving charges and magnetism. When a current carrying conductor, see here PQ, if you see, current is passing through that conductor because charged carriers are moving from P to Q. So current is passing in this conductor, and this conductor is placed inside the magnetic field. So when a current carrying conductor is placed in the magnetic field, it experiences some force. So the maximum force that is acting on this current carrying conductor, which is placed in the magnetic field, is F equals to ILB. This we have discussed in moving charges and magnetism. The force that is acting on a current carrying conductor is ILB. So that equation I am using, it is equation number 2. Now from these two equations, that means I am substituting this equation 1 in this equation. If I substitute equation 1 in this equation, we get F equals to, in place of I, what we can write? BLV by R. So write that. BLV by R into, what is this? LB. Okay, this is I, it is L. So in place of I am using this equation 1, BLV by R into L into B. So F equals to, B into B is B square, L into L, L square, V by R. So this is the maximum force that is acting on current carrying conductor after substituting this equation 1 in this equation 2. So we can also calculate the power. We know power that is required to push this arm in the magnetic field is P equals to F into V. This is the expression for power. Now we know F. So that F value substitute here. So P equals to B L square V by R into V we get. So the power that is required to push the arm is B square L square V square by R. So here why the power is needed to push this arm PQ? See, we know already. So this is a current carrying conductor. Now we are pushing this inside the magnetic field. So when it is pushed, there is a change in the X value. When there is a change in the X value, there is a change in the area, L into X. So when there is a change in the area, there will be a change in the magnetic flux. When there is a change in the magnetic flux, EMF is induced. And according to Lenz's law, that induced EMF opposes the original cause that produces it. Actually, here induced EMF is generated due to the change in the flux. That is due to change in X value, and that is due to the motion of this conductor. So that induced EMF opposes the motion of this PQ. It will not allow the further motion of this PQ. But anyhow, it has to move. So work is said to be done. Okay, what is the work that is said to be done? We have already calculated here. Work QVBL. So when there is a work, I can also calculate power. So some power that is required to push against that EMF. So that power is F into V, which is V square L square V square by R. So this power we can also calculate using another equation, which is I square into R. This we have discussed in current electricity chapter. Power is square of the current into R. So here I is what? VLV by R from equation 1. I square means V square, L square, V square by R square. So that only we can substitute in this equation. V square, L square, V square by R square into R. So this one R will get cancelled. So in the denominator we will be having only 1 R. So we get P is V square, L square, V square by R. See, we got the same expression either from FV or from I square R. We got the expression for power as V square L square V square by R. Okay. So here some amount of work that is said to be done in order to push this PQ against that EMF. That amount of work will store in the form of mechanical energy. And that energy is dissipated in the form of heat energy. This is what energy consideration. Now we'll discuss about the relation between the charge and the magnetic flux. So there is some relation between the charge and the magnetic flux. So what is that relation we'll see? So we know according to Faraday's law, E equals to d phi by dt. That only I wrote. And we also know V equals to I into R. V in place of V we can write E. So E equals to I into R. But I is what? The rate of flow of charge. I is rate of flow of charge. So the expression for current we can write dq by dt. Small q also we can write. Here I am using capital Q. I is current, which is the rate of flow of charge. So E equals to dq by dt into R. So according to Faraday's law, E is d phi by dt. And according to this equation, E is dq by dt into R. Now I can compare these two equations. If I compare these two equations, what we will get? D phi by dt equals to dq by dt into R. So here this dt will get cancelled. I can write dq equals to d phi by R. So this is the relation between the charge and the magnetic flux. Or else we can also write d phi equals to R into dq. Very simple. Okay. So this is the relation between the charge and the magnetic flux. And the next topic is eddy currents. It is very important topic. So what are eddy currents? From the name itself we can identify that eddy currents, eddy, waste currents, useless currents. So even though these are useless currents, these eddy currents are used in many applications. That is why we are studying about these eddy currents. So what are eddy currents? You can see here, when bulk pieces of conductors are subjected to change in the magnetic flux, induced currents are produced in them. Those currents are called eddy currents. What we are saying, when bulk pieces of conductors are subjected to change in the flux. So in a conductor, if there is a change in the flux, we know already according to Faraday's law, when there is a change in the flux, EMF is generated. It further produces currents. So here also the same thing, but here when small pieces of conductors are subjected to this change in the flux, in small pieces of conductors, if there is a change in the flux, currents are induced, EMF is produced, and that further produces currents. Those currents which produces in bulk pieces of conductors, when they are subjected to change in the magnetic flux, are called eddy currents. So how these eddy currents are generated, we can see using this experiment. Okay, so here you can see in this diagram, there are magnetic dipoles. This is north pole and this is the south pole of the magnetic dipole. Now there is a copper plate. See, here you can see a copper plate, and that copper plate, don't think that these are two copper plates, only one copper plate. Okay, this copper plate is suspended in the magnetic field. So here there are a magnetic dipole, means a magnetic field is generated around that. So this is a copper plate which is fixed to one end. So that copper plate is suspended in the magnetic field. And now this copper plate is allowed to swing. See, it is swinging. Okay, going to one end to the other end. So it is executing simple harmonic motion in the magnetic field. So how it executes the simple harmonic motion, you all know. So when we just displace this copper plate to one end, and if you release, it will be oscillating inside the magnetic field. So here copper plate is allowed to swing like a simple pendulum between pole pieces of a strong magnet. So when this copper plate is allowed to move in the magnetic field, what will happen? When there is a magnetic field, there will be magnetic field lines. So the magnetic field lines cutting across this area will change. So when there is a change in the magnetic field, I can say there is a change in the magnetic flux. When there is a change in the magnetic flux, EMF is induced. They further produces current. See, you can see current that is generating when this copper plate is coming to this end, current is in the clockwise direction. When it is going to the other end, it is oscillating in the magnetic field. So when it is going to the other end, current direction is reversed. So like this, currents are generated, induced currents are generated on the copper plate. And what do? According to Lenz's law, they oppose the original cause that produces it. Here currents are generated due to what? Due to the motion of this copper plate in the magnetic field. So these currents, after developing, what do? They oppose the motion of that copper plate. So the motion is damped and the plate comes to rest in the magnetic field. Okay, so it is like Faraday's law and Lenz's law only. Okay, so the currents that are generating on this copper plate, when it is allowed to swing in the magnetic field, are called eddy currents. Those currents are called eddy currents. Because of those currents, the motion of this plate is stopped. So here the same experiment you can say, but the difference between this and this is, you can see from the diagram. Here on the copper plate is like this, but here on the copper plate, rectangular slots were made. Okay, so it is the copper plate is cut in this manner. Okay, you can see here, this is zoom. Okay, so here the area is reduced. Here the area of the copper plate is this much, but here the area of the copper plate is reduced. The rectangular slots were made on this copper plate, and in the same way it is allowed to swing like a simple pendulum in between the poles of the magnet. So it is moving inside the magnetic field. And we know when it is moving inside the magnetic field, there will be a change in the magnetic flux. When there is a change in the magnetic flux, EMF is induced and that induced EMF produces current. Those currents are eddy currents. And what those currents do? They oppose the original cause. What is the original cause? They oppose the motion of this copper plate. But what is the difference between this and this? Here, the induced current is more. So they can stop the motion of this copper plate. So that is what is written here. The motion is damped and the plate comes to rest in the magnetic field. But in the next case, as rectangular slots are placed in the copper plate, the area available to the flow of eddy currents is less. Currents are produced, due to the change in the flux, but area for the flow of eddy currents is less. So what will happen? The plate with rectangular slots reduces the damping. So there will not be that much damping because these currents are less. So the plate moves more freely. In this case, area is more currents are generated because more area. So they oppose the motion of this plate. But here area is less. So eddy currents are less, and that cannot oppose the motion of the copper plate. So it can move, the plate can move freely in the magnetic field. In the metallic cores of transformers, electric motors and other such devices, eddy currents are undesirable, not required. So why? Because we know eddy currents, they develop and they oppose the motion. So these currents opposes the working of this electric motor. Anyhow, this electric motor has to work. So they do some amount of work against to this eddy current. So what will happen? Since these currents heat up the core, so currents are producing. Due to that, this electric motor is stopping, but it has to work. So it opposes those eddy currents and some work that is said to be done. When there is some work that is said to be done, some amount of energy that will be releasing. That amount of energy is converting in the form of heat. So indirectly, these eddy currents are generating some amount of heat. In metallic cores of transformers, electric motors and other such devices, eddy currents are undesirable. Since these eddy currents heat up the core and dissipate electrical energy in the form of heat. See what we have discussed in transformers, electric motors, eddy currents will generate. So these currents, what do they do according to Lenz's law? They oppose the original cause that produces it. So these eddy currents try to oppose or try to reduce the efficiency of these transformers and electric motors. Anyhow, these electric motors, they have to run. So these electric motors will perform some amount of work against to these eddy currents. So work is said to be done. So that amount of work will release in the form of electrical energy. So they produce that amount of electrical energy will convert in the form of heat. So indirectly, eddy currents producing heat. So since these currents heat up the core and dissipate electrical energy in the form of heat, these are undesirable.